AI coding benchmarks measure the code, not the spec the agent works from. SPECLAN is a free VS Code extension that turns your specifications into structured, AI-ready prompts. We benchmarked 13 LLMs and let one of them judge the rest. Code benchmarks tell us which model writes the best Python function. They don't tell us anything about the specification that got the function shipped. The upstream half of agentic delivery, the part where a brief becomes a spec and the spec becomes a prompt for your coding agent, has been flying blind. And that matters, because a downstream agent is only as good as the spec you hand it. SPECLAN's job is to turn your specifications into structured prompts for those agents, and the methodology this video proposes is one our roadmap intends to live by. A spec is good when Claude Code, Google Antigravity, or Codex can implement it without drift. Driftlessness is the property. The gallery at speclan.net/compare is the instrument. Today, we switch SPECLAN to a local LLM. Watch it generate the entire spec tree for Excalidraw on a laptop. Walk the comparison gallery across 13 candidates, and then let Opus judge the rest. Before we trust the local model to write our specs, we sanity check it. Here's LM Studio with Qwen 3.635 billion, A3B, loaded, empty chat, plain text in. A greeting back, a reasoning trace. 82 tokens per second, 300 tokens total, end of stream. The local model is alive. Now we wire it into SPECLAN. The default provider is Anthropic with Claude Opus, the canonical model SPECLAN ships with. We want to swap that out. First, the LLM configuration tab. This is where SPECLAN keeps its provider credentials. Anthropic and OpenAI keys not configured. Google Gemini valid. And at the bottom, local LLM experimental, pointed at localhost 1234, which is the port LM Studio listens on by default. Click Test. Green banner. Connection successful. SPECLAN can talk to the model. Back to the LLM model tab. Open the provider dropdown. Anthropic, OpenAI, Google, and local LLM experimental. We pick local LLM. The model dropdown now populates from the LM Studio catalog. The currently loaded model sits at the top. The rest are registered but unloaded. We pick Qwen 3.6-35B-A3B. And the model info card materializes. State loaded, context window, 262K tokens. Comfortably above the 50,000 token floor. SPECLAN's agents want quantization Q4KM, architecture Qwen 35mo, runtime LM Studio, tool use supported. Apply model. And the sidebar settings row flips. From Anthropic, model default to localhost, 1234, model Qwen 3.6-35B-A3B. The provider swap is fully applied. Next, the Infer specifications from Codebase Assistant, one of the more complex agentic flows SPECLAN ships. The goal is to take an existing codebase and reverse engineer a structured specification from it, so you can start working spec-driven on legacy code that never had specs in the first place. Our codebase is Excalidraw, the famous open-source diagram tool, large enough to showcase the assistant, well known enough that you already have an intuition for what a good spec of it should look like. Click Start Analysis. The stepper advances. Scope phase begins. The assistant starts to work. Let's speed things up. The generation is sped 149 times. The full run takes about an hour. Look at the top right of the screen. That's the macOS Activity Monitor's GPU history, showing the Apple M4 Max under load. The work is happening on this laptop. No tokens leave the machine. The scope phase generates a vision and mission for the project. Then Explore, Qwen reads its way through the codebase, file by file. Via the Explore MCP tools SPECLAN serves to the agent. The abstract phase finds 9 top-level features and rewrites them to be user-centric. And then Infer, the slow part, where the assistant creates one specification at a time. Watch the sidebar tree on the left. It fills from 0 features to 22 as the assistant works. Each entry in the activity log is an MCP tool call. Create feature, create a requirement, linking, list_goals. An hour of agentic spec generation on a laptop with the GPU bars to prove it. The codebase reads itself and writes the specifications back. What Qwen produced is not a chat transcript or a JSON blob. It's a tree of real markdown files. Here's F1722, text to diagram and mermaid. Title, description, scope, what's out of scope, and a relationship section that cross-references other generated features. A level deeper, RO167, join existing session. A requirement under the live session management feature, complete with an acceptance criteria checklist. F1592, element library management. Same shape, scope, out of scope, relationships. F0967, file management and export. Note how the out-of-scope bullets explicitly cross-link to other generated features. The assistant carved up the codebase into a coherent tree, not a flat dump. 22 features hand-reviewable, Git-diffable, ready to hand to a downstream coding agent. One model is a data point. 13 is a picture. And the local model is still loaded over there in LM Studio, by the way. That conversation didn't disappear. We point Chrome at speclan.net/compare. Same brief, same codebase, 13 different LLMs. Each spec tree is fully navigable, side by side. Before we walk it, read the fairness notes on screen. Anthropic models run to the Anthropic SDK, which adds built-in scaffolding to-do lists planners on top of the MCP tools SPECLAN exposes. OpenAI models and every local model, because local runtimes, like LM Studio, ship an OpenAI-compatible API, go through the OpenAI SDK with the MCP tools only. Same MCP surface, less SDK help. Most of the requirement count gap between SDK families is scaffolding, not raw model. And Excalidraw is in every model's training data. Your private repo won't be. Structural findings generalize. Raw polish probably won't. The default pair, Claude Opus 4.7 with a 1 million token context on the left, GPT 5.4 on the right. Opus's vision, a world where ideas flow freely through visual thinking. GPT's, sketching shared understanding for everyone. Same brief, 2 valid framings. Opus leans poetic. GPT leans utilitarian. Drill into Opus's feature tree, and you find rich multi-paragraph behavior specs, geometric shape creation, click and drag affordances, shift key proportion constraints, mid-drag corner adjustments. Drill into GPTs at the same depth, and you find broad umbrella categories, shapes, connectors, and text bundled into one feature. The names and granularities don't line up one-to-one across models. The vision is the comparable layer. Swap the right side to Qwen 3.635 billion, A3B, the local model we just watched generate. 4 goals, 23 top-level features, 49 total, 174 requirements. Vision, empowering everyone to visualize their ideas. A local model on a laptop, within 12% of Opus on requirement count. Swap to Gemma 426 billion, A4B. 3 goals, but click into the first one, intuitive user experience and customization, and the goal body shows literal placeholder text. Goal description goes here. The model created the slot but didn't fill it. Smaller open weights can drop teaching beats. Gemini 3.1 Pro Preview. The vision reads beautifully. A canvas for unrestricted visual collaboration. But look at the feature tree underneath. User identity and access. Account creation, secure sign-in. Excalidraw doesn't have accounts. The model invented a product that doesn't exist. GPT-OSS 20B. OpenAI's older open-weights model. Stats line, 0 goals. 5 top features, 16 total, 17 requirements. The feature tree is coherent. Whiteboard drawing, canvas navigation, undo, collaboration, export, but the entire goals tier is gone. Older model nails the headline, loses an abstraction layer. NVIDIA's Nematron 3 Nano, the smallest tree on the page. 4 goals, 3 top-level features, 12 requirements. Vision still reads. Granularity collapses. Back to GPT 5.4 on the right. So far, we've looked at 13 trees, with 13 different opinions about what Excalibur is. Now the question is, which of those opinions is right? We can do better than vibes. Expand the methodology notes on each candidate card, and a judgment subsection appears, written by the same Claude Opus that produced the reference baseline. The verdict sits at the top of every output. Opus on itself. Reference baseline for this comparison. 16 top-level features map one-to-one to Excalibur's real surface. 197 requirements, with consistent acceptance criteria rigor. Every other tree on this page is measured against this one. Opus on GPT 5.4, compact by a factor of 4.5 in requirements and 2.7 in features. Each top-level bucket stays at the elevator pitch level, good as a navigational overview, weaker as an implementation blueprint. Gemini 3.1 Flash. Opus's judgment. Domain mismatch. The vision talks about canvases like Opus does, but the top-level decomposition reads as a generic SaaS scaffold. System foundation, data management suite, user identity and access. 13 requirements add up to Opus's 197, 15 times sparser. Useful as evidence that a preview tier model can draft the vision but lose the plot on decomposition. Gemma 4.8 billion. Running locally via Ollama on consumer hardware. Opus's verdict. Remarkably coherent for an 8 billion local model. 3 top-level features. 21 requirements, all landing on real Excalibur concepts. 9 times sparser than Opus, obviously, but no domain drift and no structural pathologies. A strong answer to how small can the model be before the pipeline stops working. And then, Claude Haiku 4.5. 203 requirements. That's more than Opus, from a model that runs at a fraction of the cost. Opus's own judgment. Haiku earns that number by splitting what Opus treats as one requirement into 2 or 3 smaller ones. Uniquely includes a theming and localization bucket Opus misses. Acceptance criteria read more mechanical, but nothing major is missing. Haiku is genuinely competitive on specs at a fraction of the cost. That changes the calculus. Reading 13 trees, side-by-side surfaces patterns, nothing else does. 1. The density spread is roughly 17-fold. Nematron Nano at 12 requirements, Haiku at 203. Same codebase, same brief. 2. The anthropic models cluster within 3% of each other across sizes, Opus, Sonnet, Haiku, meaning size barely moves the count. The SDK scaffolding does. 3. One local model closed the cloud gap. Qwen 3.6, 35 billion A3B. On a laptop, OpenAI SDK path. Within 12% of Opus's requirement count. 4. Some models invent products that don't exist. Gemini Pro added user identity, account creation, and secure sign-in features to a drawing tool. 5. Some models can't fill the slots. Gemma 26B left a goal body as literal placeholder text. GPT-OSS produced 0 goals. 6. Different trees don't mean better or worse. They mean different products. Choosing the model is choosing the product. None of these is wrong. They are answering the same question with different answers. And we can only see that because the gallery exists. And because Opus told us where each candidate sits relative to the baseline. So where does that leave you? A spec is judged by whether an agent can implement it without drift. Until somebody builds the closed-loop benchmark, pointing Claude code, anti-gravity and codecs at every tree, and measuring what they produce. SPECLAN.net/compare is the next best instrument. You read the artifact and judge for yourself, and you can produce your own on your own machine, with your own model, with weights that never leave it, in an evening. Thanks for watching. If this was useful, leave a like. It helps other developers find the video. Visit SPECLAN.net for the full docs, the long-form blog posts behind this comparison, and the gallery itself. And install SPECLAN. It's free from the VS Code Marketplace. Just search for SPECLAN in the extension sidebar.